This video is going to be an introduction to working gas law problems. We're not going to actually do any calculations in this video, but just sort of setting the table for being able to do those calculations. Some preliminaries. We've already talked about the ideal gas constant, R, and you'll be seeing that again in one of the equations that we'll be using a little bit later. Earlier, when we talked about root mean square velocity of gases, we used a value for the gas constant of 8.314 joules per Kelvin mole. In these problems, and the problems we'll be working throughout involving the gas laws, we're going to use the value at the top of the table, 0.08206 liters times atmospheres divided by mole, Kelvin times mole. Kelvin times mole is all in the denominator. Or to 3 sig figs, 0.0821. So that's the gas constant we will become most familiar with using. But as you can see, they have different values, different units. You need to use one in other courses where it's most advantageous to you in terms of the units that you're using. The other thing to keep in mind is a set of conditions that are known as standard temperature and pressure. They're 1 atmosphere, 0 Celsius. Those are what are known as standard conditions. So like Greenwich Mean Time is where we start our time scale on the planet. These standard temperature and pressure conditions just give us a reference point. So compare from one lab to another, different values. So STP, 1 atmosphere, 0 degrees C. So mention some gas laws. There's a host of them. And I'll try to give you a hint a little bit later on when we do some calculations of how you can get around and memorize some of these. But maybe the best thing to do is just go ahead and memorize them. First one is the combined gas law. That says that P1V1 over N1T1 is equal to P2V2 divided by N2T2. Where ones mean one set of conditions and two mean a second set of conditions. So pressure times volume divided by N number of moles divided by temperature. So that's combined gas law. It's more commonly seen though if you're not holding something constant out of those, it's going to be the number of moles. You're changing the conditions for the other three. So if the N1 is equal to N2, they cancel out, and you'll see this is most commonly used as combined gas law. P1V1 over T1 is equal to P2V2 divided by T2, combined gas law. Boyle's law says that you've got a constant number of moles and you're holding the temperature present. You're holding the temperature constant. And so P1V1 is equal to P2V2. That's Boyle's law. Charles's law says with a constant number of moles at constant pressure, V1 over T1 is equal to V2 over T2. That's Charles's law. Avogadro's law says you're holding pressure and temperature constant. So if you're changing the number of moles, the volumes are going to change proportionately. So V1 over N1 is equal to V2 over N2. That's Avogadro's law. So all these laws have been, an initial set of conditions, and you're trying to find out if you change conditions, what one of these other variables will be. There's also Dalton's law that says that the total pressure of a system of gases is equal to the sum of the individual pressures of gases, the partial pressures. And this comes out of the kinetic molecular theory, and that all gas molecules just see each other as independent particles. They don't care what they are. And so the total pressure is equal to the sum of all the individual or partial pressures. Another way of thinking about this is that any individual pressure, P sub I, is equal to total pressure times this X sub I or chi sub I that you see. That's the mole fraction, or the mole percentage if you want to think of it that way. So the mole fraction times the total pressure of a system is equal to the individual or partial pressure, whatever gas that you're looking at. Then we've seen Graham's law earlier that says that the root mean square velocity of gas 1 divided by the root mean square velocity of gas 2 is inversely proportional to their masses, or they're equal to the square root of m2 divided by m1. So that's a whole bunch of gas laws where you're looking. The first set was when you're changing conditions. These other two are gases that aren't changing conditions. You're just looking at how they either add up the total pressure or they're looking at their speeds. There's another important gas law. It's called the ideal gas law. And you'll use this gas law when you don't know a certain condition, but you know all the rest, and you're not under a set of changing conditions. So the ideal gas law says that PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the ideal gas constant, and T is the absolute temperature. Always in all of these, make sure you change your temperature to Kelvin. So if we're going to use R as 0.0821 liter atmospheres, moles to the minus 1, Kelvin to the minus 1, that means you have to have pressure in atmospheres, volume in liters, and of course temperature has to be in Kelvin. Got to get those units to that. The ideal gas law falls out of kinetic molecular theory of gases, where we have these small particles, distances between them are negligible or large, their size is negligible, there are no attractive forces, and all the collisions are perfectly elastic. And so our everyday conditions that we're working at in the lab, ideal gas law works fine. However, if you're at really high pressure and really low temperatures, gas molecules can exert some attractive forces to one another, and their volume may not become negligible anymore. In that instance, there's something called van der Waals equation that we use for real gases. It takes into account the size of molecules and the attractive forces between them. And so P plus AN squared over V squared, that quantity, times this quantity, V minus NV, is equal to nRT. P is still pressure, V is still volume, N is still the number of moles, R is the gas constant, and T is the temperature. And so there's the first parenthetical portion of this equation corrects for the pressure. So we got an experimentally measured pressure, and we're adding in a correction factor, this AN squared over V squared, which takes into account the attractive forces of molecules. The second parenthetical statement, so this volume correction term takes into account the fact that molecules do have some sort of volume associated with them. And so we've got the container volume that we have, and we're subtracting out the volume of each of the molecules. So here's a table of the different constants for A and B. They vary depending on which type of gas that you're looking at. And they got the particular units associated with them so that you can add atmospheres to pressure and liters to the volume. We won't be doing any calculations with these per se, but you need to be aware that a lot of what we take in chemistry is on the very best perfect conditions, and a lot of times that isn't the way it really is. And so we have ideal gases, and then we have real gases.